our objective today is based on angles. In particular, there are some special types of angles that we want to work with. And so we're going to name and classify angles as our primary objective. And we also want to be able to determine the angle measures of angles. We will touch a little bit on construction of angles. We will not hit it in any depth at all. We'll save that for a future lesson. And we'll discuss what angle bisectors are, but we won't go heavily into how you actually construct or create. And here are the vocabulary that we will use. Once again, take a look at them and see if there is something that you don't know what it is already. Not expecting you to have them written down, but just check to see if there's something you don't already know. All right, so what's an angle? And I'm seeing a couple people drawing them with their hands, thinking of them. People know that angles look like this. And one of the important characteristics that I want you to get used to thinking of an angle, a lot of geometry has to deal with motion and how things move. One piece that you should start by thinking about is if we can start by having a ray and just say this is where it begins, we would have the ability then to take this ray and start spinning it. If we rotate it around its vertex, we can open it up, and as it's rotating, we can see that an angle is created. You rotate it until you reach the point where you want it to stop, and once you find its terminal location, or its ending location, or an angle gets created. With a lot of the things that we will do, particularly when we start examining congruence a little bit later on in the year, thinking of angles as rotations is a helpful thought pattern. Yes, I'm very aware that you already know what an angle is, you know what it looks like. But I also want to make sure that you can get it in your mind that angles are a rotation. Thinking of them that way will make other things easier down the road. In particular, it does help right away with thinking of the interior and the exterior of an angle. Just like in regular English, interior means the inside, exterior means the outside, and so we can think of these pieces as an initial ray, RT, rotated along its vertex, creating the angle SRT. But please note, as we're rotating it, the space that gets created by opening it up and rotating the rays, that's the interior. Of course, since we're going to work with angles, we need to be able to talk about them. We need to be able to communicate regarding them. And so how we name them is of course important. Looking at this, we need a way to name the angles. And as I'm sure you know, it's pretty common for people to give an angle a name, like angle number 1, and they can say angle number 2. And a lot of times people just assign them numbers, angle 1 and angle 2, just to make referencing them easier. And although there's absolutely nothing wrong with doing that, it's not going to be enough because you also need to know how to reference them using their letters. Basically, you can reference an angle just by listing the 3 points that create the angle in the order in which you draw them. So in this one, we could say B connects down to A, connects up to C. The order I go through them with my pen is B, A, C, so B, then A, then C. Please observe that I could flip that direction around and say C goes down to A, which comes up to B. What do you think? Same angle? Different angles? same angle. Like, it's very similar when we were looking at segments, how we had a segment AB. We could flip around the letters to say segment BA, and it's the same thing. We could do that with angles too. Okay, so there's one angle pair. We have the angle BAC. Let's identify another one. C can connect down to A, which can connect up to D, so angle CAD. And we should identify one more. We could take the entire wide angle. What would this one be called? What is that, sir? Angle B, then A, then D. What do you notice about all three angles? There's something in common for all of them. A is always in the middle. And it's not because there's anything special about the letter A, but with all of our letters, A was the vertex of the angle. That will always happen. If you are naming an angle, the vertex will always be the center letter. And because of that, it's sometimes common for people to want to simply say, if we have, let's say, M, P, and N, well, how many different angles do I have here for M, P, and N? Just the one. There's no confusion for this. And so it is correct to call this angle M, then to P, then to N. This is correct. It's also correct just to say angle P. A lot of times, angles are named just with the vertex and nothing else. But you only do that if there's no potential confusion. If I came up on the original problem and simply said angle A, which angle A am I talking about? The left one, the right one, or the whole combined one? We don't know. That's the point. If there's any kind of confusion where you have angles next to each other where they're sharing a vertex, we can't use just one letter because which one do you mean? We don't want people to guess. That's why we have the three-letter notation to help us communicate effectively when we've got a complicated picture. But with simple pictures, we can use a simple notation. All right, so I'll consider this then. How would you name the angles? Angle QTR is one of them. RTQ. We're going to note, that's the same angle named twice. So this would not be considered two different angles. We'll also note that this one, because they've got the number there, we could also simply say that's angle 1. All three of these are referring, wow, that was really ugly. All three of these things are referring to that angle. Three different correct angles for that one. Let's pick just one way of naming angle 2. What would you want to call angle 2? I can tell you, I would just say angle 2. It's got a number. If it's already numbered, why not take advantage of the simple notation, which is, it's right there. We don't need to worry about having some three-letter notation because it's already labeled for us. But as you noted, Jalen, if we did decide to call it RTS, that's absolutely correct. And what about the combined angle? How would you name the combined angle? QTS works. And so we've got that one finished. How many degrees are in a circle? Come on. Thank you. Yes, there are 360 degrees in a circle. Chop it up into 360 pieces, you get 1 degree. I don't expect you to have this stuff written down simply because, well, frankly, I know that you've worked with protractors in your early classes. You know the size of 1 degree. We're just rehashing the fact that degrees are used to measure the size of an angle, and that there are 360 degrees in a circle. That's all that we're rehashing. Just quickly stating stuff that you already know. We also had yesterday the ruler postulate, which said, hey, rulers are used, and you can use rulers to measure 1, 2, 3, 4. Protractors are used as measurements for angles, and you can measure 1, 2, 3, 4 degrees. Since we can use the protractor postulate to measure the size of an angle, we can instantly start classifying them. And admittedly, I'm going to run through this very quickly because this is something that I'm sure that you've seen, I'm sure that you've worked with it before, and that you've already got skills work measuring a protractor. So here we go. Types of angles. How do you classify an acute angle? It's less than 90 degrees. What about a right angle? It's equal to 90. Obtuse. Over 180, but less than 180. A straight angle is equal to 180 degrees. Something I'm sure that you're all familiar with already. Well, there's actually a fifth type that a lot of times students aren't aware of. Remember how I was talking about rays being, or angles being a rotation? If I take this one in the purple and I just start rotating it like this, I could rotate it to be an acute angle. If I keep rotating it, I could get a 90. If I rotate it more, I could get an obtuse. If I rotate it more, I get a straight angle. What if I keep rotating past 180 degrees? So what if I rotated it so that it came down toward here? And the angle that I'm talking about then is actually that one. Not the piece here. That's not the angle I'm referring to. I'm talking about if we rotated it all the way around that way. What is this one? That is actually called a reflex angle. And I don't expect you to have this particular piece memorized. I'm putting it up here mostly because we don't really use reflex angles much in, or almost at all in geometry. Geometry is the study of shapes, and when we work with shapes, we're generally concerned with convex shapes. And so the reflex angle is something that we virtually never encounter in geometry, just because we choose not to work with it. It is much more common in later maths, especially if you start considering trigonometry, if you start considering physics. Reflex angles play a significant role in later math classes, just not this one. I don't expect you to know it right now, but I did want you to have a little bit of exposure to it so that when you encounter it later on, at least it wouldn't be the first time. Okay, so let's start looking through some pieces. Angle WXV. What kind of angle is it? WXV is acute. Got it. What about angle ZXW? ZXW. Well, how big is it? It looks pretty close to 90 degrees. Visually, some people may say, okay, it looks kind of like it's 90, so I'm going to call it 90. We can't look at something and say, oh, well, that looks like 90, so it must be 90. We actually need to measure it. Beginning with this piece, Where does the angle begin on our protractor? Looking at the number, right there is at 30. Coming up, it comes toward here, ending at 130. So how big is it? Yes, you got it, McKenna. If we're going to start at 30 and rotate over to 130, simply taking an easy piece of subtraction tells us that is a 100-degree angle. So what kind is it? We have an obtuse angle. Congruent angles. Yesterday we had seen that congruent segments are the same size. Congruent angles are the same size. Now, this is a piece that I want to be very, very clear. We had discussed yesterday that you have to be careful with what you're saying are equal, and you have to be careful with what you're saying are congruent, because they're not interchangeable ideas. The same thing applies here. If you wind up saying angle ABC, and I want to rewrite that so that I can have it in a single line. If you say angle ABC equals angle DEF, this is wrong. Angles are physical objects, and it is not correct to say physical objects are equal. Equal is a word that is reserved for numbers, and angles are not numbers, they're things. If you want to talk about angles this way, you need to say that they are congruent. Similarly, though, we can talk about the size of an angle. A 30-degree angle is equal to a 30-degree angle in size, and so we use the separate notation, the measure of angle ABC and the measure of angle DEF. When we put this little m in front of the angle symbol, we're talking about the size of the angle, not the angle itself. That's where we're saying 45 degrees instead of angle 2. There is a distinction between the size of an angle and the actual physical object itself. When we use the m's, it's appropriate to say equal. Similarly, we have these little tick marks, which are curved, and so usually instead of saying tick marks, I like to call them tick arcs, because these little tick arcs as curves show us 1 matching 1 tells us they're congruent, 2 matching 2 would tell us that they are congruent, but if the numbers don't match, 1 and 2, just like segments, then we're saying we don't know it. Maybe they are, maybe they aren't, but we don't have evidence that they are the same. Just like when we were doing the segment addition postulate, with the segment addition postulate, we saw that if we had 2 segments that were right next to each other, we could add the 2 together. 3 and 5 would tell us that the total thing would be 8. Just like that, there is an angle addition postulate for when angles are next to each other. Visually, here's what we have. And this is the most important thing we need to take out of today. Being able to use the segment addition postulate was the primary tool for working with segments. The angle addition postulate is our primary tool for working with angles. Okay, using the angle addition postulate, find the measure of angle FEG. DEG, D to E to G, so the whole big angle is 115. DEF is 48. How big is FEG? What would you have to do? Yeah, simple subtraction. Because we know part plus part equals the whole. Just by subtracting, we can get our result. That angle would have to be 67 degrees, and we're done. That's the angle addition postulate. Part plus part equals whole for angles. Consider another one quickly. Please work through this one. What did you get? Or what do you get? And so what did you wind up getting on these? 121, 59, and 121 subtract 59 equals 62. Okay, so we're done. What does bisect mean? That's looking at our vocab from previously. What does bisect mean? Bisect means to cut in half. So an angle bisector cuts an angle in half. With it cutting it in half, here's the type of thing that we would work with. Keep in mind, if we have an angle bisector, that would tell us both of these pieces have to be the same. That's why I'm drawing in some tick arcs, showing that they're the same from an angle bisector. Well, here's what we would then note. If they are the same, we can create an equation based on that. We know the size of angle 1 has to equal the size of angle 2. Make sense? If you have a bisector. And so this is a piece that you will look for. Anytime that the directions tell you you have an angle bisector, that will then let you know these are the same size, and so you can create equations declaring they are equal. Well, right there we have it then. Angle 1 is equal in size to angle 2. Solve the equation. What do we get? Okay, so we could take subtract 6 and subtract 7x. Both of those cancel, so we have negative 3x equals negative 18. Dividing by negative 3, we would obtain x equals 6. And we're not done there, because the directions did not ask us to find the value of x. We were asked, how big is angle JKM? And since JKM we have known is right there, we can now just plug it in. 4 times x plus 6. Which is 24 plus 6. So it is a 30-degree angle, and we're done. And that's it for this particular lesson. This was mostly about just, do you remember the kinds of angles, and can you then use the angle addition postulate?